That we should draw correct. There we go. Focus onto the retina. Parallel rays. Kind of makes them bend apart a little bit like this, right? So that the lens will now focus parallel rays onto the retina. So we kind of decrease the curvature, right? Increase the divergence of the rays. And so that will correct for that. And that's what nearsighted, that's what these would be for, right?
Thanks for watching. If you enjoyed this video, please hit the subscribe button and ring the notification bell so you never miss an update. Leave a comment below to help grow the channel, and don't forget to smash the like button.
In lecture 24, we're going to talk about magnifying glass. This will be important for some later discussions that we have on microscopes and telescopes. So we need to really understand how a magnifying glass works. And again, I've drawn a converging lens. This would be a biconvex lens. We have two convex surfaces on both sides. The center of the radius of curvature is at the center of the lens. And I've drawn the focal points F right here. And notice that the object is closer to the lens than is the focal point. And so that makes a big difference. If we move this point back to the focal point, then what we find is an image, a virtual image, which is way out at infinity. If I move it to the left, in this case, of the focal point, now I'm going to get a real image that's inverted over here. And the farther away I move the object, the farther away the image is going to be. But I want to look at this case, whenever we're within the focal length of the lens, because in this case it's going to magnify. That's what we're going to find out here. So how do we consider this? Well, first ray we can draw for sure is the parallel ray. So if I draw a parallel ray, I'll do this as neatly as I can, we know that that is going to pass through the focus. So, okay? And for the second one, I have some choices. I could draw it through the center, or I could consider a virtual ray going through this focus, which would come out parallel over here. And I'm going to go with the one through the center. I think that's what I did in my notes. Yes, that's what I did in my notes. So I'm going to have a ray go through the center of this lens. And what we'll see, and remember, a ray that passes through the center does not bend. And so this just passes straight through. And you can see that these two rays are never going to cross. They're obviously diverging. So where's the image? These are never going to cross, so we're not going to get a real image, a real inverted image over here. So where is the image? Well, what we can do is we can take these rays and we can kind of back propagate them and get a virtual image, which is going to form back here somewhere. Remember, dotted lines mean virtual rays, except for this one, which I made is the optical axis. And then we have to bring this one back as well. Kind of line those guys up like this. And so what we find is that the virtual image, right, is going to be right here. It's magnified, as you can see. It's bigger than the original object, and it's non-inverted. So let's put in some numbers. Let's see, what do I have here? We can use some simple numbers. If we assume that the focal length F, remember F is always the lowercase, the focal point, who I always use is the uppercase. Let's set that equal to 1 centimeter. And let's pick as D sub O the object distance to be 1/2 of a centimeter. So it's halfway in between the focal point, and the lens itself. From the previous lesson, we found that the magnification would be equal to the negative of the focal length divided by D sub O minus the focal length. Well, that's going to be equal to minus, focal length is 1, D sub O is 1/2 minus 1, which is equal to minus 1 over a half minus 1 is minus a half, so we get a 1/2 down here, which is equal to plus 2, right? Because the dividing by a fraction is the same thing as multiplying by its reciprocal. So we get a magnification of 2. And my drawing looks roughly like that's the case, because I was kind of a little bit careful here, putting focal points in the right position. So that's the magnification of it. What do you think would happen if we move the object closer to the focus? What if instead of 1/2 centimeter, what if we did like 3/4 of a centimeter? What do you think is going to happen with the image? Anybody? Well, we can either draw a picture or we can plug in some numbers, right? If we move this back, what would that do to these rays? The ray going to the center would be closer to this line here. The angle would decrease between here and here would decrease, right? As I go farther away, which would cause this line to be moved back like this, whereas this ray is going to be virtually the same, right? If I move this back, the parallel ray is still going to hit right here, so this ray is not going to change. What is going to change is where they cross. It's going to move the crossing back farther, which means it's going to cross at a higher point, which means the magnification is probably going to go up. But let's just try it out. Let's let d naught, let d sub 0 be equal to 3/4 of a centimeter. What does our magnification equation say then? Well, it's minus, still 1. This time it's 3/4 minus 4/4, which is going to be minus 1/4, so that's going to be plus 4. You see? So the closer the object is to the focal point, the larger the magnification.
Okay.
The closer it is to the lens, the smaller the magnification.
Okay.
This is very similar to what you would see if you looked in, say, a spherical concave mirror, like what you use to, put on your eyeliner or trim your mustache. It's the magnifying mirrors, right? We had one up here last week when we were doing reflective optics, right? And you saw when you put your face really close to it, you kind of looked like it was the same size face, but as you moved back, your face got bigger. You could see, much finer details, like on your nose or mustache or eye or whatever.
Yes.
Remember that?
Yes.
Yeah. And then when you got at the focal length, something weird happened. It got all strange. There was nothing you could see. It was a blur. And then as you moved back farther, you saw yourself upside down. So that's neat. In this case, right, you then as you move beyond the focus, now you're just creating an image over here, and that's what we talked about a couple of lectures ago. All right, so thinking about the magnifying glass, if I move the object closer to the focus, staying within the focal length of the lens, though, then it's going to get bigger and bigger and bigger.
Okay.
All right. And the image will be a virtual and non-inverted image, which means if I'm looking from over here, right, if this is my eye, it appears that the object is back here and bigger, right? So this is a magnifying glass. You hold your eye up to this. You obviously want to get close enough that the spread, this angle, right, the rays don't go outside your eyes. You're not going to be able to hold it from really far away. You have to kind of get close to it. We're not going to talk about these details too much, but you get the idea here. If you're close enough to it, and you move the magnifying glass such that the object that you're looking at is pretty close to the focal point, then it's going to look really big. So you can look at ants, things like that. And this can only be done with converging lenses. We're not going to talk a lot about diverging lenses, with one exception, as we'll talk about them when we talk about different types of eyesight, when we talk about farsightedness and nearsightedness.
Okay.
All right, that's it for this one. So, lecture 25, we're going to talk about telescopes. Not in any great depth, but we'll talk about them a little bit just to try to understand them. And the first thing you should realize when you're talking about a telescope is that telescopes look at faraway objects, really far away. If something's really far away, right, whenever I draw the rays coming out of them, which I can go in all directions, right? If I trace this out really, really far away, some point very distant, like way over here, then all of the rays that arrive at this point, which I'll move, will appear to be parallel. Even another ray around it, right? So, over great vast distances, like distances across galaxies and stuff like that, the rays coming from distant sources appear to be all parallel. So, if I think about what does a lens do if all of the rays come in parallel, again, let me draw my positive lens like this. All the rays that come in parallel, what does that do? Here's the one going through the center. I'll say that the focus is here. Passes straight through because that's going through the center of the lens. And all of these other rays will, without moving focus, pass through the focus. So if they're all passing through the focus, if we wanted to say magnify that, because we know they're not all really passing through the focus because objects are never infinity away, right? That's the case if they're infinity away. If they're not quite infinity, they're a little less, which I know sounds silly, but by a little less, I mean they're just really, really far away, so that you can think of them as approximately like that. What will happen is, so over here I've already drawn a picture where I've got a big lens here, which we're going to call, by the way, the objective lens, and its focal length will be this distance right here. We'll call that FO for focal length of the objective lens. That's to this point right here. So you see the rays that all come in parallel all get focused to the focus. But if they're a little bit not parallel, then what's going to happen is they're going to form an image just behind this focus.
Yes.
So, for example, this ray, which came in, should have bent. I don't know why I drew it like that. It should have been, sorry, almost parallel. So I'll kind of accentuate the not parallelness of it. See how that is coming in not quite parallel, but almost to the optic axis?
Yeah.
It's gonna, and then this is a ray that's going directly through the center of the lens, so it doesn't bend at all. And it too has a very small angle that it makes with the optical axis. So it's almost parallel to it, but not quite. And so you can see that it's going to focus back here. So if we want to make that image bigger, we already know how to do that.
Yes.
So the way to think about compound lenses, that's when you have more than one lens together, is you first work the first lens, okay? You find out where the image is, okay? Here's the image. It's going to be right here. Now for the second lens, this is another positive lens, but it's of a shorter focal length. So this one, I want the focal length to be less. All right, so I'm going to just get a dotted line down here so we know where this is going. So that's this one. This one is going to go here. And so that we'll call F sub E for eyepiece. This we call the eyepiece. So this eyepiece has a shorter focal length lens. I'm going to make this focal length line up with the focal length of the objective lens. This one is longer, but I can make them overlap by simply putting the second lens of the eyepiece, F0 or F0 or FO rather, plus FE. Add the two focal lengths together. That distance will be the distance that the eyepiece is from the objective. You see that?
Yeah.
And if I do that, what am I doing? Well, whenever I have a lens with a focus F and I image an object, in this case it's an inverted object, right? We already know what happens. If this inverted object is closer to the lens, then the magnification is about 1 to 1.
Yeah.
But if it's really, as it gets closer to this focus, the magnification increases, right? Remember the virtual images that we drew.
Yeah.
So I can draw them again by considering this ray. I have to make the lens a lot bigger though. And so that would be like that. And then we can go, of course, through the center. It won't bend. And so all I have to do is backtrace this and backtrace this until I get way back here. And now I've got my non-inverted image. And it's inverted here because the thing we were imaging was already inverted, right? So it's going to stay inverted. So there's my virtual image. So when I look at it from over here, these rays coming out seem to be coming from this point back here. So I see what appears to be a much larger version of this thing just beyond my focal point. So it's important, remember, that you want it to be over here because it's in this region. Whenever your object distance is less than your focal length, that's when you're acting like a magnifying glass. And so the eyepiece is actually a magnifying glass. And so I've drawn the non-parallel rays in purple, forming the cross right here. So that's my little image of whatever this distant object is. It could be a planet, you know. It could be Saturn. Saturn's nice to look at in a telescope. So you can see the moons. And its image is going to be right here, but it's pretty small. It's inverted, so it's upside down. Nothing I can do about that immediately. But if I put a magnifying glass such that the focus of the magnifying glass is beyond where the image is, then it's going to magnify. Actually, if I just get my magnifying glass and I move in on that image, I'll find a spot that works for me. I'll get the magnification that I find convenient or pleasing. But these are usually fixed, and so they fix it such that the focal length of the eyepiece coincides with the focal point of the objective lens, because anything that's not infinitely far away is going to form its image over here in this region, right?
Okay.
And so if the eyepiece is set up such that its focal length coincides with the focal length of the objective, then we'll always be able to magnify whatever image we get here.
Okay.
Make sense?
Yes.
And so in that sense, a telescope is really just, think about a lens. It images just like lenses do, and we've looked at that a few times.
All right.
And then we add the magnifying glass to it.
Okay.
That allows us to enlarge that image. Now it'll be upside down, but you wouldn't know it, right? How do you know that you're looking at Saturn upside down versus right side up? It's not like you can tell. But if somebody had sign on Saturn, and from their perspective it was right side up, it would look upside down from here.
Okay.
You can fix that, by the way, by replacing this converging lens with a diverging lens. They'll have negative focal lengths, and so you can flip the magnification on. But that's a more advanced kind of problem. We're not going to worry about that. Mainly, I just want to get across the idea of what a telescope is and how it works. The objective lens will be a long focal length. Okay, you want this to be a long focal length.
Okay.
And I'll let you think about, maybe I'll put a homework problem together that asks why do you want it to be a long focal length. Some aspects of telescopes we're not going to get into this year. And this is, we're getting a little deep into the optics stuff, and I didn't really want to go too deep into it. I just wanted to, see some insightful principles from this principle of least time, right? See how these simple laws can tell you things about complicated objects. All of this can be done without any mathematical equations, by the way. You can use rulers. That's the nice thing about ray optics. You can just measure it on paper. If you're careful in the way you draw things, you'll be able to predict and measure what these image sizes are and stuff like that just from using these very simple principles. So there are other considerations that will lead you to say things like, well, the larger diameter this lens is, right, is going to be better. And the way to think of that is, well, you can collect more light. Distant objects, like the light is faint. If you want to collect more light, right, by using a bigger lens. And professional telescopes owned by universities and the government, National Institute, I don't know, what's NRA, I think it's called. That's radio telescopes. I can't remember the organization, but they usually use reflective optics, but these are big. I don't know what the largest telescope that you can buy is that's using refractive optics. So here I'm talking about refractive optics. You of course could design a telescope using reflective optics too. Copying this down, huh? Okay. Mainly you should try to be able to reproduce it just by thinking about it. So we've got a really long focal length lens here, right? And then a short focal length lens here, right? That's going to act like our magnifier.
Okay.
And I will write down for you. So what does the magnification turn out to be? FO over FE. Okay. And so here is kind of, I'm not going to derive it. It's not that hard, but it's not important for what we're doing. So here, if you want to make the magnification really big, since these are both positive lenses,
yes,
these focal lengths will be positive. Okay, so these are converging lenses, convex lenses and stuff, right? So these are both positive focal lengths. So, but if we choose a long objective lens focal length and a very short eyepiece focal length, you see that this magnification gets bigger. Okay, so that's why these two are as they are. But I think if you draw pictures, you can kind of see, why that would be, and that's something that you should definitely explore. All right, so next we'll talk about microscopes. Okay, so lecture 26, we're going to switch from telescopes to microscopes. Now, I'm sure you're all familiar with what we usually use microscopes to look at, right?
yes.
And what's the difference between what you would do with a microscope versus a telescope in terms of the objects that you're looking at? So, for example, the objects that you're looking at with a telescope are usually very
Big.
far away.
Yes.
And, well, yes, big, right, I guess. You look at small things if you wanted to that were far away if you had a really good telescope. But an interesting problem, by the way, might be to reason through the idea, why is it you can't see the American flag on the moon using a telescope?
It's on the opposite side of the moon.
Well, no, it's on the right. It's on the side of the moon that we always see. But why can't we see it with a telescope? So it's an interesting problem. You can know roughly how big a flag is. It's not one of the giant flags they use. It's one of these normal size flags. But you could reason through what kind of telescope would you need, right, in order to see something of that size at that distance away. Okay, and maybe I'll make that a homework problem. So that sounds like a good one. Yeah, so with telescope, we look at far away objects, right?
Yeah.
That's why we made this approximation that the rays were coming in almost parallel to the optical axis of the lens, right? Therefore, the focal length of the objective should overlap with the focal length of the eyepiece, right? So that the eyepiece will now function as a magnifying glass for it, okay? So, microscopes, on the other hand, do we look at far away objects with microscopes? No. When we look at things with a microscope, right, we put the object very, very close to the microscope objective. So, it's a two-lens. Well, in truth, you can have more complicated microscopes, correct for chromatic aberrations and stuff like that. But a simple microscope would just need two lenses, an objective lens and an eyepiece, just like the telescope. The difference is that the objective lens and eyepiece focal lengths are both very small. So when we think of the object that we're imaging, right, it's going to be very close to the objective lens. Now, do we want it to be, what side of the focus do we want it to be on? Do we want the object distance to be less than the focal length or greater than the focal length of the objective lens? If we made it less than, then all we've really done is we made a magnifying glass. And we know there are limits to that, okay? You can't see, cells with a magnifying glass. Because in truth, with a magnifying glass, you can't see anything any bigger than what you'd be able to see if you just put it up to your eye, right? So how big do I see things with a magnifying glass, right? Well, it will be as big to my eye as it is when I put it here. The problem is, and we'll talk about the eye later in a lecture coming soon, when I put the magnifying glass between my eye and the object I'm trying to look at, right, this thing on the paper, this little cube here, appears really big. But if I put the magnifying glass here, it's going to appear the same size, but I'll be able to see it. I'll be able to focus on it. That's what the magnifying glass does for me. So I can't hold a cell close enough to my eye to see it, right? So this is a little bit different. It's not a magnet. This objective lens is not acting like a magnifying glass, right? Instead, the focal length, the object will be beyond the focal length, and we will image it with this lens. And its image will appear somewhere over here, right?
Yes.
Inverted as usual, because it's a real image. Now I'm going to use an eyepiece to magnify this even further, you see? So the arrangement of the lenses is different than before. The separation between the lenses for an astronomical telescope was the focal length of the objective plus the focal length of the eyepiece, okay? For a microscope, it's the focal length of the objective plus the focal length of the eyepiece plus some additional distance L. I think it's usually called the barrel length. And that is really for realistic purposes of, how tall do you want your microscope to be and how tall are people. And if you had a really tall microscope, you'd only work for really tall people that could stand up and look into it. So this distance tends to be dictated by the height at which people stand and when they bend down to look, okay, and table heights and stuff like that. So this is what you get, okay? The eyepiece is still acting like a magnifying glass, right? Because real images will be just, it's set up such that the focal length of the eyepiece is, in truth, it's going to be a little bit less than what I drew here. It'll be, something like here, right? And so this is just acting like a magnifying glass. And as it turns out, the magnification for this is a little more complicated than what we had with the telescope. So negative, of course, there's a negative sign because it's still inverted. And it's going to be minus L over F naught times 25 centimeters over FE. This 25 centimeters we'll talk about when we talk about the eye and how the eye works. This is called the near point of the eye, and that's the distance in which humans can focus on an object in front of their face. For a kid, it might be more like 7 centimeters, and for an old person, Grandpa Joe, it might be 200 centimeters, but 25 is just like the standard that people use. And so this has to do with where is the eye going to be in relation to the microscope. You can imagine an eye. Well, that's not very eye-like. An eye out here, right, looking. You see that L is not all that important. What you really want to do is make the focal length of the objective and the focal length of the eyepiece very small numbers.
Yes.
The product of two small numbers is a really small number, and so when you divide a big number by a really small number, you get a good magnification.
Okay.
Of course, it would be nice if everyone was 12 feet tall and we could use much longer barrel lengths. but not essential. So, this is the microscope. The big difference, telescopes, objective lens is a relatively long focal length lens. It's relatively flat, if you've ever seen these.
Yes.
The eyepiece is a short focal length lens. Microscope, both the objective and the eyepiece are short focal length lenses.
Okay.
Understand?
Yes. Yeah.
Awesome. Enough said then. So lecture 27 is on the eye. We're not going to do a lot of derivation or mathematics in here. We're just going to cross a couple of basic ideas. And this will kind of be our final lesson on, applications of optics or whatever, right? And then we'll have another lecture where we talk a little bit more about the theory before getting ready to move on to the next set of lectures on Newton's laws next week. Light enters the eye through a variable aperture called the pupil. The variable aperture, it has an iris which can control the amount of light that is let into the eye. If you've ever seen an iris, they're kind of unique. They close uniformly into a circle. It's focused by the cornea lens system onto the retina, which is the back surface of the eye. There, light is detected by rods and cone cells, which convert the light into electrical energy, or electrical signals rather, that are transmitted along the optic nerve to the brain. So one thing to note, the image on the retina is upside down, so we're actually perceiving everything upside down, but our brain knows how to correct for this, and so we perceive everything as right side up. So that's taken care of computationally. Here we have a real picture of an eye. Right, so you can see the cornea. It's this surface up here. Okay, and there will be a question on your homework assignment related to this, where I give you the index of refraction of the cornea, and I ask you the question, why is it you can't see clearly underwater without goggles? And so you'll get to think about that a little bit. The lens is this system, this structure you see right here. You can kind of see where the iris is, and then the pupil here in the center, right? And then the retina is all of this surface back here, right? And there you can see the optic nerve. And I think some of you have tried this experiment where you close one eye, focus on a point, and then move your hand around until your finger disappears partially. There it goes. My finger disappeared. Weird. That's a blind spot you have because of the optic nerve, right, which is a point on the actual retina. When you have an object that is imaged at this portion of the retina, you won't actually be able to see it because there are no rods and cones there. That's where the optic nerve is. Focusing is accomplished by the activity or the action of the ciliary muscles. You can see them kind of in this diagram here. They look like a fibrous bundle attached to the edges of this lens. And if they tense up, they will pull and flatten that lens out. The relaxed state of the eye is when you're focusing on an object in the distance. So if I have an object, here is my eye. Yes, I think it's exactly the opposite of what I just said. This is far away versus, say, close up. So this is relaxed. No need to engage any muscles. This is tense. So when objects are closer, it's in a tense state. The focal length of the eye, kind of F max, is about 2.5 centimeters. The focal length under tension is less than F max. That's why we call it F max. And I'll put a problem in the homework set that allows you to calculate what that focal length will be. Now, if you get closer than a certain point, we call it the near point, right? Then you will no longer be able to focus on that object. That's because there's a limit to how much we can contract our muscles. This is called the near point. It's variable. It depends on the age of the person. So for a 10-year-old like yourself, probably somewhere around 7 centimeters. For a really old person, grandpa or something, 65 or so, maybe 200 centimeters. Not necessarily the average, but the value that we usually use for the near point is 25 centimeters.
Okay.
And that's the 25 centimeters you guys saw in the microscope equation for the magnification of a microscope the other day. There was a 25 centimeters in there, right?
Yeah.
Divided by the eyepiece focal length. That was that 25 centimeters was from the near point distance. So the reason that this near point distance increases over time is because of a loss of flexibility of the lens.
Okay.
So just like when you get older, you can do that little skin test where you pinch your skin and see how fast it falls away, and as you get older, it'll get slower and slower. So there's a kind of a loss of resiliency in your cells as you age. And so I think that's the reason for the loss of flexibility of the lens is coming from something like that. You have a question?
When you prick your skin, if it goes down slowly, I heard from a doctor that means you're dehydrated.
Well, that could be the case, but let's assume that you have normal hydration levels. As you age, that response time of your skin will go down. And I don't think it's because old people are dehydrated, but yeah, so if you decrease the focal length, what does that mean about the curvature of the lens? So if the focal length is decreased, let's think about a long focal length lens. What would that look like? They look almost flat, right? So we can imagine that we've got very little curvature there. Whereas, you might have the focal length way out here. Whereas a very rounded focal length lens would have a very short focus. And so, how do you think about that? Well, you think about the circles again, right? So if I draw, say, a tight circle like this, radius, that's where the focal point is. If I draw a very, and remember, we're only going to use that portion of it, which is, we're only going to use this portion of it for the mirror, but if I have a very large circle, then the focal point is halfway between there. You can see that the focus has gone out. And so that same segment through here, right, will be relatively flat compared to here. So we say that the curvature is increased as the focal length goes down. And so that's why it is that when you tense up your eyes, it's kind of increasing the curvature of this lens, or making it more rounded, right? And that's decreasing the focal length. So it's actually the opposite of what I had always thought, but that's okay. All right, finally, let's talk about vision corrections. I'm just going to erase this little bit here. There are two general terms you need to know. Far-sighted. And so we always measure this with respect to the relaxed eye. I'm going to draw a very simple eye with just a lens. There you go. And we're going to have parallel rays coming in. Parallel rays, of course, are going to converge on the focus, right? And they'll cross at the focus. And if this focus, with parallel rays, focus behind the retina, then this is called farsighted.
All right.
So what you can do, the corrective action that you take for this is to introduce a positive lens, or a convex lens. So let's put the correction lens, positive lens. And so you introduce a positive lens, which will start this guy to converge a little bit earlier. It kind of helps the lens in your eye out. I've exaggerated the degree to which it does that, and that will allow these guys to now move the focal point for parallel rays. Parallel rays are things that are infinitely far away, right?
Yeah.
To on the retina where it should be. Parallel rays should focus on the retina. And so by introducing this positive lens, it will decrease the focal length by adding to the curvature. Decrease the focal length to the point that it focuses onto the retina. And so that's what those do. And those kind of glasses, they tend to be like this. So they're kind of magnifying glasses. So if you if you look at the the camera a little bit, look at my eyes, so they should appear to be a little bit bigger as I pull these out. See that, I think again. But these are spherical biconvex lenses, and they're basically magnifying. I think I might be able to image the backlight. Yeah, see, there you go. Yeah, the focus is to a point like this. Now, the next case would be what is called nearsighted. Nearsighted. And that is where parallel rays focus before the retina. Okay? Focus before the retina. And so the correction for that, negative lens or divergent lenses. So if I introduce a divergent lens, try to draw, I'm going to exaggerate the curvature on this, but that's not very good either. Let me try one more time. I like that better. That's a little better. Introduce a diverging lens before the eye lens. What we'll get is the correction that we need, except we should draw it correctly. There we go. Focus onto the retina. There. Parallel rays kind of makes them bend apart a little bit like this, right? So that the lens will now focus parallel rays onto the retina. So we kind of decrease the curvature, right? Increase the divergence of the rays. And so that will correct for that. And that's what, nearsighted, that's what, you know, these would be for, right? And so these are actually, you can't really tell by looking at them necessarily, but they are you know, concave, biconcave lenses. Actually, these are progressive lenses, so I'm not exactly sure how they do that, but it allows you to correct for both so that I can, you know, read things that are close up and see things that are far away at the same time. All right, so that is the eye. I thought it would be nice just to put a little bit in because we all have eyes, and now you know how they work, basically. Okay, and we tied it back in for with the optics that we looked at, right? So, any questions?
No. Yes, what is that plus next to the lens?
Positive lens, right? So it's with positive curvature, right? Positive focal length. So the the biconvex lenses we call positive lenses. They have positive focal lengths, positive curvatures. The divergent lenses, also these are convergent, meaning they focus together. The negative lenses are divergent. They have negative focuses and negative curvatures, and they diverge light.
Yeah.
So if I have, we haven't talked a lot about these, but if I have a divergent mirror, what happens, right? Parallel rays will get sent out like that. Okay?
Yeah.
So, okay. And that's all for that. So next week we're going to move on and discuss Newton's laws. But before doing so, I wanted to revisit Fermat's least time principle. And why are we going to do that? Well, so I want to give you some reasoning that you may be able to apply to what we learn next week with Newton's laws. So I put back up the table, Ptolemy's data from 140 AD and Snell's fitting of that data. Just want to point out what he actually fit. Usually you see this written a certain way, but really this is the way to look at it. And even more properly, it's a ratio of sines of the angle of incidence to the angle of refraction. And what Snell found was that when he took the sine of 8 degrees and the sine of 10 degrees, right, he would find that he got a constant here. So really, Snell's law was an observation that if you take the sine of the angle of incidence to the sine of the angle of refraction, then you get a constant in. And if we're going from, say, material 1 to material 2, when we observe this refractive angle, then we could call this in 1, 2. And so what I want to do now is consider three possibilities. Basically, air interacting with water. So we'll say 1 is air. I'm going to write this a little bit bigger. I noticed in rewatching some of these lectures that the writing is a little small, hard to see. So we'll say 1 equals air. And so here we would, of course, have angle of incidence, and we would have our refracted angle, theta sub r. And then 2, I'm going to let that be equal to water, H2O. And so this would be characterized by an index in 1, 2, which is the ratio of the sines of the angle of incidence and angle of refraction. Also consider an interface between air and, say, material 3, which we'll call glass. Right? Again, have a refracted angle, some incident angle. Right? And finally, we can make a third measurement between water and glass. This would be in 1, 3, and this we could write as in 2, 3. Now, just using Snell's law, right, there's no reason to suspect that in 1, 2, in 1, 3, and in 2, 3 are connected in any way whatsoever. However, using Fermat's least time principle, we can actually make a prediction that they are connected in a meaningful way. And so how does that work? Well, we can write that in 2, 3, this third measurement, right, the refractive index that I observe when I go from water to glass, that index can be written as the ratio of velocities. Because remember, under Fermat's principle of least time, right, the index of refraction is the ratio of the velocities. So this is the velocity of light in water over the velocity of light in glass, and that's what this index represents. But we can rewrite this, so we'll say, you know what, we can take V2 over V3 and multiply that times V1 over V1.
Yeah.
Because that's just 1. You can always multiply anything times 1. That's the velocity of light in air, divided by the velocity of light in air, which of course is going to be 1. I can rearrange this, however, right, to be like this. V1 over V3 times V2 over V1. It's just association.
Yes.
But this is the same thing as V1 over V3 divided by V1 over V2. Because when you divide by a fraction, you can multiply times the reciprocal of that fraction instead, right?
Yes.
So all I did is just flip V2 over V1, turn it into V1 over V2, and switch this to division. But this is just V1 over V3. I'm going to write the fractions a little bit differently now, right? Over V1 over V2.
Yes.
And by this convention, right, N12 is equal to V1 over V2 under Fermat. N13 is V1 over V3. And N23, of course, is V2 over V3 using this principle of least time, this idea that light travels at different speeds in different materials, right?
Yes.
V1 over V3, well, that's just N13. And V1 over V2, well, that's just N12. And so what do I have in the end? I have this relationship, which we did not have under just Snell's law, that N23 is equal to N13 over N12. Which means that if I know the index of refraction in this one, N13, right, when I go from air to glass, and I know what it is when I go from air to water, then I can predict what the index of refraction is going to be, or really the ratio of these signs, right, for water glass, okay, which I could not do before. So it falls out directly from that. And that, you know, is surprising if all you know is that, if all you know is Snell's law. But under Fermat's principle of least time, it makes sense, right? And it makes sense because of this argument about the ratio of the velocities, right, being equal to the index, so the ratio of the indices.
Yes.
So we have a new prediction. And so this kind of reasoning will be useful next week when we start on Newton's laws. But I just wanted to revisit this and point this out to you before we move on so that you can have that in mind. And so when we start talking about ratios of accelerations next week, we should be thinking about Fermat's principle of least time and be reminded of the thing that he found there. So that means that there's some intrinsic material property
Yes.
about material 1 and material 2, and material 1 and material 3. And if you know this intrinsic material property for 1 and 2, and also for 1 and 3, then you can predict through some equality what the relationship of 2 and 3 will be, you see?
Yes.
Any questions on that? That's pretty much all I have on this. This closes out our discussion of geometric optics, where really we wanted to iterate the idea that there's this simple principle that light is this thing that travels in straight lines, and that the only time it bends or changes its course is when it encounters a material interface, and the material that it's entering travels at a different speed. The light travels at a different speed in that material. Then we'll get some bending. But other than that, it's just straight line.
Okay.
And we'll find when we get to Newton's laws and we start talking about particles instead of light, that these things will follow much more complicated trajectories than straight lines.
Okay.
So that's why I wanted to spend some time talking about geometric optics. No questions? All right. We'll close this out then.